Okay, so the difference between standard deviation S and standard error. So I put this in here because in my last class I didn't talk about chapter 9, and it'll also not hurt you guys to do it, but I think you guys have a better handle on this. So the sample standard deviation, like as in this S thing, this is that thing we calculated back in chapter 2. And this talks about how much variation there is in a sample. So like how many what proportion lie between blah and blah. And the formula for S is this big old square root sign, sum xi minus x bar squared over n minus 1. Do you guys remember that formula?
Yeah.
Remember, it's kind of painful to work with, right? Oh, and I missed one thing on it. Do you see what I missed? It's okay if you don't.
Squared.
Yeah, there's supposed to be a squared here. And that's so that you don't have positive errors canceling out negative errors. Does that idea make sense? Mm-hmm. Okay. And this estimates how the sample values vary relative to the mean. So this is stuff like 68% of people fall between a height of 5'6" and 5'8" for women, like for the whole population. The standard error of x bar, what is that formula? It involves that S. S over square root of n. Very good. Okay, so this tells us the standard deviation, or an estimate of the standard deviation of x bar, which tells you how much the mean is going to vary if you took many samples of the same size. Okay, so this measures the accuracy of your estimate of x bar. So that's the basic idea. But you get that this S is always bigger than this guy? Okay. So this tells you how much variation you have in samples of the same size versus just how much variation is there going to be in your population. Okay. Okay, here we go. This is the next thing you have, right? So suppose you find the mean number of hours of TV watched per day is 2, with a standard deviation of 1.5 hours. Find the standard error of the mean and describe what it means. Assume the sample size was 175. Okay, so 2, what is the statistical notation for 2? This is the mean number of hours of TV. So x bar, yep. We've got an estimate of x bar, or an estimate of our mean mu, which is x bar equals 2. And the standard deviation of 1.5 hours, what's that telling you? That's S, yep. The sample standard deviation is 1.5. The standard error of x bar, oh, I hate it when I do that. So annoying. Oh, look, I fixed it. Okay. So, oh my God, guys, apparently I didn't sleep last night. So standard error of x bar is equal to S over root n. So 1.5 over root 175, which comes out to be 0.113. Okay, so that's the standard error, and like tell me what it means. So the kicker here is that you have to talk about the fact that you're repeatedly taking samples of the same size. Does that idea make sense? So if you were to take many samples of size what?
175.
Of size n equals 175. And find x bar for each one. This is an estimate of the standard deviation of that distribution. Or this estimates, I don't know what I had there. Estimate of probably standard deviation. I don't know why this eraser defaults to ginormous.
As soon as you make big mistakes.
Standard deviation. Or this estimates the variability in X bar. So kind of like what it's saying is if you take these samples and you find X bar for all of them, how are those X bars going to how are they going to change? How different are they going to be? How spread out are they going to be? Okay. So this confidence interval stuff that we're doing for this lesson is very much like the previous stuff, except for the standard error formula is different. Other than that, and also what the multiplier is different, right? Because you got to use what kind of table? The t-table thing. Okay. And you have to know that, okay, means t-table, proportions z-table. That's something you'll have to recognize. I won't tell you which one to use. You have to figure it out. Okay. So here's the idea. If you were going to measure a quantitative variable, like height, for all units in a population, what's the mean? And then how much is this mean going to vary over all samples of a given size? And then to address that variability, we're going to find this confidence interval, which will estimate how much that mean is going to vary. So here's the general format. So the general form, we've done this before, is the sample statistic. So sample statistic plus or minus some multiplier times the standard error of your sample statistic. What's our sample statistic in this case if we're talking about means?
X bar.
X bar, good. Which is the mean of all the numbers in the sample. If you're talking about proportions, that sample statistic is p hat, right? Okay. The multiplier, which is t star, is found using the t-table, and you have to account for this whole degrees of freedom. Do you remember what that was? And minus 1. So sample size minus 1. And as your sample sizes get bigger and bigger and bigger, these T stars get close to the Z stars. Pretty much once you go over 30, you're almost at the exact same number. And the standard error is found using the formula SE of X bar equals S over root N, where S is the sample standard deviation, which is usually given to you in some kind of data output. Will be an example today where we actually find it, because it's just to remind you how. And then N is the number of individuals in the sample. Okay. Do you guys have your t-tables with you? Awesome. If you could get them out, that'd be lovely. If you don't have one, and also forgot to put these out, if you need a copy of the notes, I have extras as well. I really admit you've been working without one this whole time. Okay, so what are the degrees of freedom going to be? Yep, this will be DF equals 21. Okay, so 21 actually, and we will have a 98% confidence level. So in your 21 column, go over to 0.98. 2.52. And how about if that confidence level changes to 0.9? 1.72, yep. This is a good time to bring up that quiz question. So there was a quiz question where I asked you, if you do something, is your confidence interval's width going to increase or decrease? So what happens to the width of a confidence interval when the confidence level goes down? Well, it narrows. Does that make sense why? So because the multiplier and the standard error affect how much you add or subtract, right? And how much you add or subtract, that makes how wide the interval is, right? This number getting smaller makes the number you add or subtract smaller, which means your interval is narrower. So on that question, what I was looking for is the reason that your interval gets narrower, as most of you got was like narrower was the right thing to say. I just wanted you to say that the multiplier gets smaller, and that's what happens. Versus the second question, where when your sample size increases, it's the standard error that gets smaller.
So as T star goes up, the interval becomes narrower?
Yes.
Okay.
Because like say if you did like, pick a number like 0. What's 0 plus or minus 2.52? It's negative 2.52 to positive 2.52, right? What's 0 plus or minus 1.72?
Oh, so it goes up.
Yeah, you see how this, like, if you were to like graph it on a number line, this one's going to go from negative 2.52 to 2.52. This one's going to go from negative 1.72 to 1.72. That would be if you had a standard error of 1 or something like that. But assuming you had the same sample size, you have the same standard error, right? So that's, and assuming it was the same sample. Okay. So in each case, use the information to compute a confidence interval for the population mean. So the first thing you should do is find your standard error and your multiplier. So the standard error of x bar equals s over root n, which is what, 6? Which is 6 over 4, or 1.5, right? T star, what's your degrees of freedom? Okay, great. We're at a 90% confidence level, so look for the T star associated with 15 degrees of freedom for that confidence level. 1.75, beautiful. Okay, so then your confidence interval is x bar plus or minus T star times the standard error of x bar, which is what, 76 plus or minus 1.75 times 1.5. Do you buy that? Or that gives us 73.4 to 78.6. I definitely did some rounding there. In essence, that's, other than having to find a different multiplier in a different way and finding this thing a different way, it's not different than the previous stuff, really, is it? It's just different formulas, but same general structure. Okay, this guy. Did the standard error change?
No.
The confidence interval.
The confidence level did, yeah. So SE of X bar is still 1.5, but your T star will change. Will it get bigger or smaller? Bigger. Okay, so I found that this T star was 2.13.
Yep.
Okay. So will this confidence interval be wider or narrower than the previous one?
Wider.
Wider because of that T star. So 76 plus or minus 2.13 times 1.5, or 72.8 to 79.2. Yeah, to be more confident, you need a wider net. That's kind of the idea. Does that make sense? Okay. So as the confidence level increases, keeping the degrees of freedom the same, the value of blank increases, meaning the interval's width is blank. So as your confidence level goes up, what goes up? The T star value. Meaning the interval's width is going to increase. Yes, thank you. Help me English. As the degrees of freedom increase, keeping the same confidence level, the value of something decreases. No, well,
No,
we keep the same
standard
confidence
error.
level, so the standard error decreases. Remember, that's because standard error of x bar is s over root n, right? If you have the same sample standard deviation and your n is just getting bigger, that number gets smaller. Okay, and then the degrees of freedom results in a smaller value of t star. Wait, what am I saying? It doesn't relate to c star at all. So X-nay all that, okay? Which gives a more precise or narrower interval. We assumed we had the same confidence level, so. All that stuff.
It does relate to T star.
But we want to keep the same confidence level. Oh, that's right. I don't know what I'm on today.
Pen, I need to bring a pencil.
I'm so sorry.
I love pen.
Yeah, because in addition to that, if you have more degrees of freedom, you also get a better T star, don't you? Yeah, so it's also a narrower interval. So I'm so sorry. I was thinking about the proportion stuff, and for the proportion stuff, we use the same multiplier no matter what, right? But for this thing, in addition to your standard error decreasing, your T star also decreases. So it kind of helps on both fronts. I know, crazy. Okay. So a couple of conditions required to use T for the confidence interval. So if you're doing a T test in like real life, you should try to do these. I had a friend doing a T test with like a sample of 5, and I was like, my stats book says you should have 30 things. Go make more measurements, Patrick. So the population of measurements needs to be bell-shaped, and in that case, you can make a random sample of pretty much any size, but I mean, making a sample of 2 seems like a really silly thing to do. And for small samples, the data should show no extreme skewness and probably shouldn't contain outliers, which will drastically affect your t values you get. And the best thing to do is to pick a large-ish random sample, and your book defines large-ish as n bigger than or equal to 30. So. Okay. And then the book proceeds to do a bunch of stuff where n isn't bigger than or equal to 30. So, happens in life too. So one question you should ask yourself for this class, if you look at a study, is be like, what was the sample size? Was it bigger than 30? Yes or no? And then if it's less than 30, just be a little bit skeptical. Don't doubt everything, but be a little skeptical. So each man in a random sample of 9 of men aged between 30 and 39 is asked to do as many sit-ups as he can in 1 minute. And the mean number of sit-ups was x bar equals 26.2, and the standard deviation number of sit-ups was s equals 6. Find the value of the standard error of the sample mean, and then write a sentence that interprets this value. Okay, so what is SE of x bar?
It's 9 divided by...
Almost.
I'm sorry, 6 divided by square root of 9.
Great, which is equal to 2. Okay. So over many samples of size n equal to 9, the standard deviation of the mean of these samples is about 2. So approximately 68% of samples will have a mean between 24.2 and 28.2, that kind of stuff. Okay, but we're talking about what's going to happen. Look what the x bar is going to look like. Find a 95% confidence interval for this mean. Okay, so I think we already know what SE of x bar is, right? We do need to find t star. How many degrees of freedom do we have? Yeah, terrible. So it's going to be a big T star number. 2.31, yep. So your confidence interval is X bar plus or minus this T star times standard error of X bar, which is 26.2. Somebody must be a marathoner that they put that there. Plus or minus 2 times 2.31. So that's 26.2 plus or minus, what, 4.62? Which gives approximately 21.6 to 30.8. Who thinks they could beat those guys that sit up in a minute?
Police officers.
Yeah, I think they're police officers?
Yeah, well,
Do police officers suck at sit-ups?
I know, because the state troopers, the requirement is at least 30 in a minute.
When I was on the UAF ski team, I could do 60.
Yeah.
Yeah,
And my highest is 102 in a minute.
yeah. So, I mean, that's awesome.
That's not a
Sit-ups
lot
or
to me.
crunches?
Oh, probably sit-ups.
They say
They say sit-ups.
They say sit-ups.
Anyhow, go home and test yourself for a minute and see if you're better versed in this sample. It'll be loads of fun, okay? I can make you all do that, and then we could like find a confidence interval for you guys. Okay, nobody thinks that's fun. Okay. All right. So interpret this. So I would like you to, in your interpretation, state your confidence level. So with 95% confidence, the average number of sit-ups a man can do in a minute in a sample of n equals 9 will be between 21.6 and 30.8. I was slightly picky on the confidence interval interpretation you had in your quiz. That one was a difference in two proportions. There was a question about headaches in two different age groups of women. One was 30 to 39, one was 20 to 29. And in that case, the number that you found, because you did the higher number minus the lower number, tells you how much more people in the one age group experience headaches than the other. Does that make sense? That people that were a little bit older had more headaches. We can blame it on the kids.
Yes.
Yes, exactly. I don't have kids, but I can imagine that they cause headaches. Yeah, I believe that. Okay. Here we go, another one. So this book loves this zinc question. So volunteers who developed a cold within the previous 24 hours were randomized to either zinc or placebo. 25 participants took zinc and 23 took placebo. The mean overall symptoms for the zinc group was 4.5 days with a standard deviation of 1.6. And for the placebo, the mean overall duration was 8.1 and the standard deviation was 1.8. Find a 95% confidence interval for the mean overall duration of symptoms. Everybody took zinc lozenges. So here we're just looking at the zinc people. So for the zinc people, what is X bar? 4.5. What is S for this group?
1.6.
And what is the sample size for this group? Because they're actually different, right?
124.
This one is 20. 25 took zinc,
Oh, yeah, 25.
so 25, which means your degrees of freedom is,
Oh, well, one's spelled out, the other one's not.
I'm sorry, yeah, one is actually written in words. I'm not sure why I wasn't consistent. Okay, I'm sorry. But you have to actually read.
Oh, no.
Okay. All right, so look at your table. Does it have 24 as an option?
Yes.
So what's your T star value then?
2.06.
Do you guys agree with 2.06?
Mm-hmm.
Okay, awesome. So we have the confidence interval is X bar plus or minus T star, standard error of X bar, 4.5, plus or minus 2.06 times, we didn't find the standard error, did we?
No.
Sorry, SE of X bar. That will equal
1.6 over square root of 25.
which comes out to be 0.32. So this ends up being about 3.84 to 5.16. And I will be really, really flexible about your rounding. I mean, because if I don't specify, I can't be mean, for one. And if, I know for the last section, there were sort of accurate representations of Z star, and then there were less accurate representations of Z star. If you obviously use the more accurate version, I'm not going to dock you because your answer is more accurate than mine. Like, it's okay. Okay, so if you're in the zinc group, you'd expect the mean length of cold to last between 3.84 and 5.16 days. That's like a range for what the average is you'd expect to see. I think we're going to do the same thing for the placebo, right?
Yeah.
Okay. So in this case, what's the X bar?
8.1.
8.1. Great. What's the sample standard deviation? Mm-hmm. So that group had more variability than the other group, right? Bigger number. What is the sample size? 23. So the degrees of freedom is 22. And our T star is a little bit different than, I think I got 2.07.
Yeah.
Okay, great. Okay. And we still need the, great. 8.1 over root 23, which I got was approximately,
1.8.
oh, thank you, it is 1.8, yep. Okay, I have the little eraser out for little mistakes, although that was kind of a big mistake. 1.8, I got 0.38. But me making mistakes is good because it keeps you on your toes, right? To actually think. It'd be better if I did it on purpose and then it was like,
I have
planned.
friend who's in stats and her teacher does that.
Makes them on purpose?
And won't say anything until the next slide, like, y'all are idiots.
Oh, well, I definitely,
Like,
yeah.
that's not a good strategy.
That's a strategy. Okay, so now our confidence interval is X bar, which is 8.1, plus or minus the multiplier, which is 2.07, times the standard error of 0.38, which is 7.31 to 8.89. Do you notice anything about those intervals?
You don't contain any of this.
They don't overlap, do they?
No.
Like one goes from 3.84 to 5.16, or one goes from 7.31 to 8.89. So the means are actually different then?
Yeah.
Yeah, that's kind of what this next question is saying. On the basis of the intervals that you found in A and B, is it reasonable to conclude that taking zinc lozenges reduces the overall duration of a cold more than taking the placebo?
Yes.
So yes. As the two intervals do not overlap, the mean duration of cold, I don't know, cold length or whatever, is probably different between the two groups. Okay. And then the last question says, in their paper, the researchers say that they checked whether it was reasonable to assume that the data were sampled from a normal curve. You can do this by like graphing them and see if they fall kind of bell-shaped. Does that idea make sense? Okay, and you could make Excel do that for you as opposed to having to draw the bars by hand. And is this relevant in our calculations? Like, what part of what we did meant you really should check that? Hint, are the sample size is big enough? No. So that's kind of the idea here, is that if your sample size is less than 30, you should really graph your data to see if it's bell-shaped. So the answer we have here is for small samples of n less than 30, it's necessary to verify that the population has a normal distribution. Not everything does. Like if you were to say take, I don't know, house prices in Fairbanks as your population, that curve ends up looking a lot like this, because there's lots of dinky cabins that aren't worth very much money. Like, and there's a large concentration of them, and then there's big houses that have like rather large values attached to them. Does that idea make sense? Okay. All right, now we're going to also talk about paired differences. So paired differences, in essence, this stuff is the exact same as what we just did. The only difference is that your data come from, first you have your data, and then you find the differences, and then you work with those differences. So the data values that you take, like your before and after measurements, they're used to find the differences, and then you ignore them. Does that idea make sense? Okay. So the data are two variables for each of the n individuals or pairs. So it could be before, after, mother, daughter, father, son, whatever. And you've got a table of x, a column of x's, a column of x2s, and then a column of differences where you've done some kind of subtraction. The population parameter, the mean of the differences, so that would be mu sub d. Scratch that part, okay? This time I actually mean it. Scratch that part. Okay. The sample statistic, the way we notate this is just with d bar, just to emphasize that they have come from differences. Scratch the equivalent to, because I'm not even sure if my equivalent to is correct. So I'm going to plead the fifth and just leave it off. The standard deviation of your sample, just to emphasize it's come from differences, this is going to be S sub D. Standard error is SD over root N. And then the confidence interval, instead of X bar, it's D bar. D bar plus or minus some T star multiplier you find times the standard error of D bar. So we'll do one example where we're like already given a lot of the information, and we'll do one example where we actually have to find the differences and then work with them, okay? All right. So a researcher was interested in knowing whether the mean weight of the second baby is higher, lower, or about the same as the mean weight of the first baby for women who have at least 2 children. Okay, so what I think a reasonable guess might have been that second children tend to be heavier. Was that true for anybody that had kids? For second?
My second one was definitely heavier.
Okay. I don't have any kids, so I have no idea, but.
I was a lot lighter than my sister.
Okay, so it was probably going to go both ways, like sometimes, right? But the question is, does it go one way more often than the other, right?
Yeah.
Okay. Like my sisters were all like lighter than me, but my sisters are twins, so they were premature, and so yeah, you have twins, you don't have a sample that will work this way. Okay, so this researcher found a sample of 40 women who'd had at least 2 children, and then she found the difference, like the mean difference was 5 ounces. She did the first weight minus the second weight. Does that mean the first baby was heavier or second baby was heavier? Second. She did first minus second, so that would actually mean the first baby was heavier. And the standard deviation of the differences was 7 ounces. So, okay, so write the mean of 5 ounces and standard deviation of 7 using appropriate statistical notation.
Wait, does that mean that some babies were 12 ounces heavier than their sibling?
Some babies were negative 2 ounces.
It's on the label.
That formula that gets you the sample standard deviation gives you an estimate of what happens in the population. So it was not observed that that happens. Like, it doesn't actually occur that but I don't know, some babies might be 12 months of it. Like with my sisters, with my sisters, I was 6 pounds, they were 4. So it can happen, right? That is more than 12 ounces heavier, right? As opposed to, and then if you came out negative, that actually has meaning, right? If this result is negative, that means that baby 2 is heavier, which also happens, right? So yeah, totally possible that both those things could happen in a sample if you have lots of variability, and the variability will come from, a preemie first, a regular baby second, or vice versa.
Or just 2 regular babies.
Or just-
Mine were.
Yeah, I mean, that also could happen, but the difference there probably is not as acute as 5 pounds and, 3 or 2 or something. Maybe it is, if you have a 9-pound baby, whatever. So moving on. The point is, the mean of 5 ounces, instead of X bar, you use D bar. Does that make sense why? Because it came from a difference. And then for 7, instead of S, I use S sub D. Okay, find a 90% confidence interval for the parameter that you defined in part B. Okay, so we have D bar is equal to 5, SD is equal to 7. What was the sample size? So the degrees of freedom is, which I realize is not actually on your table, okay? So if you look there, you have the closest thing is 40. So let's just use 40's multiplier. So we're going to use T star equals 1.68. If you're halfway in the middle, like suppose your DF came out to be 35, you could reasonably average those two. Does that make sense? But once you're closer to one number, just pick that numbers. Okay, and we also are going to need the standard error of D bar, which is SD over root N, which is 7 over root 40, or I got 1.12. So then our confidence interval is this D bar plus or minus our T star times SE of D bar, or 5 plus or minus 1.68 times 1.12. So I got 3.12 to 6.88. Do you buy that?
Yeah.
Yeah? Okay. No? Okay, awesome. And this 90% confidence interval is not the standard. That is actually like a little bit lower confidence than normal. 95 is really common, and sometimes you have to go higher for reasons we can discuss a little bit later. So draw a picture illustrating the confidence interval you found in part B. So all this is asking you to do is to make like a number line and tell me where it falls. So I have like 2, 3, 4, 5, 6, 7, and the confidence interval goes from just above 3 to almost all the way to 7, right? And what you suspect or hope is that the true value of your D bar or your mu sub D falls within that interval. So how come you can use this to conclude that the weights are actually different, and possibly the first baby is usually heavier? So first baby, because 0 is not included, which means they're probably not the same, right? Why would the first baby being heavier? Because it's all positive, right? If you do first minus second and get a positive number, the first had to be bigger, right? So this suggests that on average, the first baby tends to be heavier. Maybe it's because you're running around chasing that one. You can't gain weight. I don't know. Who knows? But that's what this data at least suggests. Okay. That previous one was nice because they already gave us what the standard deviation and the mean was, right? This one is a whole page because it doesn't, okay? It'll take a little bit to do this problem. So we have a random sample of just 5 college women, and it's just 5 to keep the arithmetic reasonable for you guys. Obviously, bigger is way better for like real life situations. And they're asked for mothers and daughters' heights, and they want to know whether, on average, college women are taller than their mothers. And here are the results in inches. So the thing is there's an obvious pairing, like you pair a daughter to their mother, right? So we need to add in and find the differences, what I'm going to call the D's. And the difference we're going to find using daughter minus mother. So for pair number 1, what is daughter minus mother? 1. So daughter 1 is 1 inch taller than said mother. Pair number 2, 3. Pair number 3, -1. Meaning in that case, pair number 3, the daughter's shorter. Number 4, 3, and number 5, 3. Okay. Now we're going to forget about this table, and we're going to use these things, the differences, to do all of our calculations. So our parameter of interest is D bar, which is daughter height minus mother height. Your book does a good job telling you what order to put stuff in just to keep your answers all the same, because if you switch the order, you're going to get the same number, just negative. And I'll do the same thing on your quizzes, so please pay attention and listen to directions. Okay, so that's the first part. Now, find the 95% confidence interval for the parameter you defined in part A. So the first thing that you need, the very first thing, a number of these, is you need D bar, which you don't actually have. So how's you going to find D bar? Average the differences, yep. So our differences were 1 plus 3 plus -1 plus 3 plus 3 divided by 5. This is just a regular old average. So that comes out to be 1.8. Does that make sense? Okay. The next thing you need, if you're going to find the standard error, you need this standard deviation, right? I think I told you I'd do one ugly problem that had you redo this calculation, right? So this is that big old square root formula. And it's the sum of the DI minus D bars over n minus 1. Why did I use D's instead of X's? Because it's differences. Okay, so the most common mistake you guys made when you did this kind of questions on your own was you forgot the square root sign. Just put it there and then, add it in at the end or something like that. So our first difference was 1, right? You got 1 minus 1.8 squared. What was your second difference? 3 minus 1.8, right? Squared. What was the next difference? Minus 1.8 squared. And how about the last two?
3.
Both 3. All divided by 4. Okay, when you work that all out, you end up with 12.8 over 4, or approximately 1.79. Your calculators are pretty smart, as in you can punch this in one go as long as it doesn't get too long. Just put parentheses around your entire numerator, and then everywhere else I drew them in, it'll be fine. And don't forget the square root sign. Okay. So once we found D bar and ST, then I think we're in pretty good shape to do the confidence interval, right? All right, so the next thing that we need for the confidence level is the multipliers and stuff, and the standard error, right? So what is T star going to be? What's my N? 5, so degrees of freedom is gonna be 4, okay. So that's a pretty crappy degrees of freedom, 2.78. I made a mistake in my notes. I didn't actually find the standard error. I used the standard deviation, which is terrible. So the standard error of D bar is SD over root N. So 1.79 over root. And could somebody please tell me what that is? Because I don't have a calculator and I didn't actually do it. Actually, I might have a calculator. Someplace. 0.800.
Yeah.
Do you guys agree with that? I got 1.79 divided by square root 5. I got 0.8005. Yep, so let's just go with let's just go with 0.8 just to be simple. Okay, then your confidence interval. So D bar plus or minus T star times the standard error of D bar. Which is 1.8 plus or minus 2.78 times I got negative 0.42 on the bottom end, did you? And then I got 4.02 on the upper end. Okay. Okay. So the second step is the most tedious, ugliest of all, though, right? Okay, but it's just good review, because you probably have to do it in your final at some point in time. That's how I can sneak it in there, right? I can ask a prerequisite question and also like have you do a confidence interval, so I kind of test like chapter 2 and this chapter at the same time. That's efficiency. Okay, so using the interval in B, write a sentence or two about the relationship between the mother's heights population, mothers and daughters, that is. So with 95% confidence, daughters are between, okay, so instead of saying negative 0.42, that negative means 0.42 inches shorter, right? To 4.02 inches taller than their mothers on average. From this confidence interval, could you conclude that that they're actually different? No, because it technically includes 0, right? But what do you think led to it including 0? What thing could you make better to probably get a much better increase your sample size? Exactly. So there are 2 things the researchers could do to obtain a narrower interval. The first thing that you could do is increase your sample size. This is going to decrease both the standard error and your T star thing, right? The second thing you could do is you could lower your confidence level. Although I feel a bit like that's like cheating. Doesn't it? Like, higher confidence is definitely better, and lowering the confidence level to get the results you want just seems kind of deceitful to me. But you could, it would work, okay? Doesn't mean it's a good thing, but it would work. Okay, so that's it.